Alright guys, I am back. Sorry for the confusion at the end of the last video. I had to take a call from my wife. But I'm back to finish out Chapter 4, and like I said, this is going to be pretty short. There's just a couple of little things I want to mention about alkanes, their reactivity, and their chemical properties. Alright? First thing I want to talk about is oxidation and reduction. Redox, right? And you guys have talked about that quite a bit in previous chemistry classes, both in college and in high school. What I'm going to do is I'm sort of going to expand on that and how we really look at it from an organic chemistry point of view. All right. So let's start off with the definition of oxidation and reduction. All right, and I'm going to start off with the traditional definition that you guys are probably aware of. If I were to ask you, what's definition of oxidation? What happens to something when it's oxidized? Well, hopefully you'd be able to answer it, but most people would say, when something is oxidized, it loses, come on, draw the E, there we go. It loses electrons, okay? And conversely, you've learned that when something is reduced, that it gains electrons. And that is a good definition for general chemistry because you do see a lot of atoms that will strictly transfer electrons from one atom to another one, right? You see a lot of ionic compounds. However, you know, it's not just the blatant loss of electrons. It can also be the loss of a hold on electrons, right? I've mentioned before the concept of electron density, right? Where you still might have the same number of electrons in an outer shell, but maybe the atom isn't holding on to it quite as tightly. All right, so I'm gonna expand the definition here, and I don't know why I drew the semicolons because that's not what I meant to do. All right, what we can say for oxidation is that when an atom is oxidized, it loses electrons or electron density. When something is reduced, when an atom is reduced, it gains electrons or, you guessed it, electron density. All right, so let me illustrate what I mean by this. I'm going to draw a series of compounds. Let's say that I have, whoops, there we go. Let's say I have this. Let's say I have, come on. This. I have this. And I have this. All right. So what I want to do is I want to take an examination of the oxidation state of each one of these molecules. All right. And to do that, what I'm going to do is I'm going to look specifically at this carbon for each one of these because that's where, the different bonds and the different attached groups changed. All right. Now, if you were to count the number of electrons held in the outer shell by each one of the carbons I've circled, in each case, they're going to be 8, right? So that carbon has the same number of electrons in each structure. However, it doesn't necessarily have the same amount of electron density, right? Look at the number of bonds to electronegative atoms, right? For example, over here on the left structure, if I were to draw out all the individual bonds, I'll do it. That has 3 H's attached to it. So this has 3 bonds to H's and 1 bond to another carbon. None of these atoms are electronegative. So that means all of these electrons here are pretty equally shared between the respective atoms and that carbon, right? However, if we look at the second structure, it's got 2 bonds to hydrogens, 1 bond to carbon, but it's also got a bond to oxygen. And you know that oxygen is very electronegative. So the electrons that are in the bond from carbon to oxygen are not equally shared. They're sort of floating over this way. Not fully. Oxygen hasn't completely taken them, but it's got a better hold on them. And that means that this carbon has a partial positive. And that partial positive only gets stronger as we have more and more bonds to electronegative atoms. In this third structure, right, we have 2 bonds to oxygen. So we also have a partial positive. In the third one, we have 3 bonds to oxygens. That's also got 1. And in each case, when we're making more and more bonds to oxygen, or anything electronegative really, that increases the magnitude of that positive charge. As we get more bonds to electronegative atoms, you lose more and more electron density. So, if we were ranking these, and we said like most oxidized equals 4, and most reduced equals 1, it would look like that. Okay? So, and this is more or less a preview. Being able to have this skill will provide useful later in later chapters where you're having to recognize whether over the course of a reaction you've oxidized something or reduced something. So, not necessarily in terms of transfer of electrons, but in terms of changes of electron density. Okay? All right. So there's one more thing I want to talk about, and that's reactions of alkane. Reactions of alkanes. Simply put, alkanes don't do much. They're kind of boring as far as reactions. There's really only 2 major types of reactions that you're going to see that they're involved with, one of which we're not going to learn about until Organic 2, and that's free radical halogenation. The one we're going to talk about right now is combustion of alkanes. And what do we mean by combustion? It means we're going to burn them. Yeah, that's what combustion is. You're burning stuff. All right. In general, it's very simple too, and it's a very predictable pattern that you can always remember. You always take, when you combust something, you take an alkane, you react it with oxygen, and this can just be oxygen in the air, in the presence of a flame, and you always get the same products no matter what the alkane. You always get CO2 and water. The only thing that's going to change is the balancing of the equation, right? You guys have all heard of methane, and you probably, hopefully know that methane is highly flammable. Well, that's because you can combust it with oxygen. So you take some methane, you burn it in the presence of oxygen, you get CO2 and H2O. If we will go through and balance the equation, put a 2 there and a 2 there. We could take cyclohexane, right, which looks, vastly different from CH4. But really, again, react it with O2, put it in a flame, you get CO2 and H2O. Very, very predictable. To balance this one, we'll need a 9 there, a 6 there. Whoa, that's an ugly looking 6. Sorry about that. 6 and 6 here. Alright. So, yeah, it's pretty predictable, but congratulations, this is your first official organic reaction that you've learned, and you'll have many, many more to follow. Alright. That ends Chapter 4, and that ends the material for your first test. I do plan to have a review at least one review session. I actually had one this morning. Guess how many people came? 0. That's fine. There was a Zoom meeting. I'll have at least 1 or 2 more Zoom meetings to review if you have any questions. Or you can just send me an email, come by my office, whatever. All right? Happy studying, and see you later.